You ever see a robot arm on a factory line welding a car door with just perfect accuracy? Or one of those bottling plants filling thousands of bottles a minute and not spilling a single drop? Well, the magic behind all that is precise, controlled motion. And the secret ingredient? It's the servo drive. So today, we're going to pull back the curtain on these amazing devices.
All right, here's the game plan. We are going to hit every single one of these topics, because I know they're critical for your exams. We'll start with the basics. What even is a servo drive? Then we'll get into the really crucial part, how they sense what they're doing. We'll look at the two big players there, resolvers and encoders. And finally, we'll see how the whole system talks to each other. Let's do this. So let's kick things off with question number one. What really makes a servo drive so special? How is it different from just a regular old electric motor? Let's get right into the one concept that changes everything. You know, it all boils down to this one word right here, dynamic. See, with a normal motor, you're just thinking about changing speed. But a servo drive is all about how fast and how accurately it can make a change. It's about snapping to a new position or speed instantly and perfectly on command. That's the whole ballgame.
And that incredible dynamic performance gives you some serious firepower. We're talking about lightning fast, super precise control over everything. Speed, where it is, how much force it's applying. And they come in all shapes and sizes, from tiny to massive. Plus, that high overload capacity, that's what lets them do those powerful, snappy start and stop moves that are all over modern automation.
But you know, that incredible precision doesn't just happen. It's not magic. A servo drive has to know, down to the tiniest fraction of a degree, exactly what the motor is doing at every single millisecond. And that brings us to the absolute heart of servo control, the feedback loop.
Seriously, just think about that for a second. If you tell a motor, hey, go to this exact spot, how does it know when it gets there? How does it know it didn't go too far or not far enough? This is the core problem that these feedback systems were invented to solve.
And this right here is the answer. An open-loop system, that's like throwing a dart with a blindfold on. You just let it go and hope for the best. But a servo uses a closed-loop system. It's like you're watching the dart the whole way. You send a command, you get instant feedback on where it actually is, you compare the two, and you're constantly making tiny corrections. That's how you hit the bullseye every single time.
So, how do we get that all-important feedback? Well, we use these special sensors that are bolted right onto the motor shaft. And their job is to turn that physical motion into an electrical signal the drive can understand. The two main players in this game are encoders, which speak in digital, and resolvers, which speak in analog. Let's dig into both.
Okay, first up, let's talk about the resolver. You can think of this thing as the toughest nails old-school champion. It's an analog sensor, and in some environments, it's just completely unbeatable.
Now, rotary transformer might sound a little intimidating, but the idea is actually pretty clever. As the motor shaft spins, the resolver's insides create a changing magnetic field. This generates two unique, smooth analog signals, a sine wave and a cosine wave. By looking at the relationship between these two waves, the drive can calculate the shaft's exact angle with incredible precision.
So here's the bottom line. The thing you got to remember about resolvers, they are built like tanks. They have a really simple brushless design, which means there are hardly any parts to wear out. This makes them the go-to choice for really nasty environments, places with tons of vibration, crazy high or low temperatures. Basically, anywhere a more fragile sensor would just give up. All right, now for the other side of the coin. Let's talk about the digital genius of the family, the absolute encoder. If the resolver is the rugged workhorse, the absolute encoder is the super smart precision specialist that, and this is key, never ever gets lost. But to really get why absolute encoders are such a game changer, you first have to understand the massive weakness of their simpler cousins, what we call incremental encoders. See, they just send out a stream of pulses as the motor turns, basically just yelling, I moved again. But they have one huge critical flaw. And boom, there it is. That's the Achilles heel. If the power goes out, even for a split second, an incremental encoder gets total amnesia and has no clue where it is. So when the power comes back, the whole machine has to do this slow, time-consuming homing process to figure out where it is again. And in a factory, that's just money down the drain. So let's put them side by side, because this makes it crystal clear. The incremental encoder is just counting steps from zero, but the absolute encoder is different. It has a unique digital address, like a fingerprint, for every single possible position of the shaft. That means even if the power dies and the machine gets moved, the second it wakes up, it knows exactly where it is. Instantly. No homing needed. Okay, pause right here. Pay attention. This is a classic exam question, and it's a concept you absolutely have to know. What is that one, single, game-changing advantage? It's that it retains its position information even after a power loss. It never ever gets lost. You've got to lock that one in your brain.
All right, we've got our drive, we've got our motor, and we've got our feedback sensor giving us the info we need. But how do they all talk to each other? And more importantly, how does the main brain of the factory tell them what to do? That's where process interfaces come in.
The big technology here is called the field bus, and I love this analogy. It really is the nervous system of the whole operation. It's a digital network that connects all the pieces. The main controller, that's the PLC, all the drives, all the sensors. Instead of having a giant, messy bundle of 1,000 different wires, the field bus lets everything talk to each other over a single, fast, reliable connection.
And of course, there isn't just one type. There are tons of different field buses, and each one is designed for a specific job. For something really important and time-sensitive, like controlling a high-speed robot, you'd use a super-fast network like Profibus DP. But if you're just connecting a bunch of simple on-off switches, you can use something cheaper and simpler, like AS interface. It's all about picking the right tool for the job.
And this is where it all comes together. Let's just walk through the whole loop one more time. Step 1. The main controller sends a command over the field bus. Step 2. The drive zaps the motor with power. Step 3. The encoder or resolver immediately reports back what actually happened. And Step 4. The drive compares what was asked for versus what happened and makes an instant correction. This whole cycle happens thousands of times a second. It's just relentless. So, as we wrap this up, here are the big ideas, the stuff you gotta have in your notes for that exam. Number 1, servo drives are all about dynamic precision. 2, they achieve this using a closed-loop system. 3, for tough jobs, you use a rugged analog resolver. 4, when you absolutely positively cannot lose your position, you need an absolute encoder. And 5, the whole thing is connected by the field bus communication network. Got it?
Which kind of leaves us with one final thing to think about. We've just seen how these systems can achieve a level of precision that's way beyond what a human can do. And as they keep getting faster, smarter, and even more precise, what's next? What delicate, intricate task that only human hands can do today will be mastered tomorrow by the perfect, tireless motion of a servo? Kind of makes you wonder, right?